Looking at 3.5, it's been a lot of using our rules and properties to simplify these. And now today we're going to start throwing in the equal sign, which anytime you got an equal sign involved, typically what's your directions now? Solve. Yep, solve for the variable. Okay, so that's what we're looking at here for this first one. Our equivalency, b to the x is equal to b to the y. What's true about x and y here? They have to be the same too. So it implies or means that x must be equal to y. So we've been working with this scheme before. Base of 4 and a base of 64. I think we got a nice number here, right? 64, can that be written with the base of 4? 4 to the what? I think it is to the third. I think somebody said it. Got our base of 4. Therefore, 2x minus 3 must be equal to that 3. Again, solve, which means we need to solve for the variable. 27 and a third. Kind of ugly at first because we got this fraction, but 3 would be a good number. So maybe I could rewrite that 1/3 with a 3. How so? 3 to the -1. Yep. We're not used to going that way, but recall 3 to the -1. Negative exponent rule. We can get rid of it by bumping it down below. So yeah, anytime you got the reciprocal, it's a -1 rule. This 2 minus 5y can just stay up on top. You know, this 27 can be rewritten as 3 cubed. Now what? Power to a power, what do we typically do? Multiply, right? Let's not write that. Well, first of all, we can do this in the same step. That's fine. Power to a power, we're going to multiply. So we're going to take this 3 times all of the 2w plus 5. And yeah, we got this common base here. So 3 times 2w plus 5, -1 times 2 minus 5w. Algebra from there. Minus 5w. Minus 15. When we get into logarithms, you know, you get busy, you start learning all the rules and the properties, and sooner or later students start asking the question, okay, why in the world do we even need these, right? How are they going to benefit us? What's the use of them? And, you know, I don't want to say finally, but SP2 is a really good example of, okay, this is why they created logarithms, or one of the main reasons, in my opinion, as to why we can use these. 5 to the x is equal to 83. 83 is not a good number. You know, it's not like 25 or 125. So this scheme that we were doing before, not going to work for us. We need to come up with an alternative method to solving for the variable when it's in the exponent. And we really don't have a lot of options, right? We can't take the square root of it or the cube root of it. Okay, we could only do that when it was like x squared and then we'd square both sides. So that's not an option. So if there's anything you take away from today's lesson, it's this. When the variable is in the exponent, that's when you want to use logs. Okay, so method number one, we can take the log of both sides. So log of 5 to the x is equal to log of 83. You know, if we've got 1 is equal to 1, then the log of 1 must be equal to the log of 1, true? Same thing if it's x, if x is equal to x, then the log of x must be equal to the log of x. Okay? So that's what we're doing here. And now what do you suppose we want to do with this x? Yep, this is where that power rule is really nice, because that allows us to bring that x down, and it basically brings it down to the same playing field as everybody else. Before it was up in the exponent, and it's like, all right, how do I move you? How do I get it down? Because again, I don't have a technique. I don't have anything to use to get you on the same playing field. Take the log of both sides. Now we can use our power rule. Now it's down here. Now I know what I can do with it. I can just divide both sides by the log of 5. And now it's just calculator work at this time. Log of 83 divided by the log of 5, 2.75. So that's method number one. I'm going to show you another way you can do this. Another way we could go about it is converting it to log form. So recall, if I have some base raised to the x is equal to y, and I convert it to log form, you just did this on your quiz. How did that look? Well, the base stays the base of the logarithm. The y gets brought over, and then our exponent goes over there. So if we do the same thing here, okay, log of base 5, that's the base of the exponent, the base of our log. The 83 comes over now, and now we set it to that exponent of x. And once again, by converting it to log form, what it does is it takes the exponent and brings it down to the same playing field. Now we can work with it. We can now use our change of base if we wanted to. Once again, if you got something as simple as a TI-30 calculator, you know, that'll definitely handle it for us. Once again, if we had our calculators, the TI Inspires, we could just plug in the log base 5 of 83 and get our answer of 2.75 again. But this example right here is kind of the heart of logarithms, in my opinion. Being able to solve an equation when the x is in the variable. Number one reason as to why we use it. Okay, so we're gonna ramp things up a little bit. Looking at 3a, 400 plus 10 raised to the 4x minus 1 is equal to 63,000. Beautiful. A little bit of inverse operations here, a little bit of logarithms possibly. Want to start chipping away at this x and getting it by itself on the left-hand side. So I see this 400 that can be moved over. So let's go ahead and subtract 400 to both sides. So it's better now. We do have a base, we have an exponent, we got our equal to, just those three things. We can choose either method we want to. You know, maybe we'll go back to just converting it to log form. If I convert to log form, and I like it because base 10, I'll go ahead and write it anyways so that we see it. Log base 10 of 62,600 is equal to the 4x minus 1. We'll deal with that 4x minus 1 here in a minute. But there's no variables here on the left, so we can just type that into our calculator. You're probably going to get a decimal, and that's okay. 4.8. Add 1 to get to 5.8. Divide by 4, divide by 4. B, we've got another one here. 100 equals 700 times e raised to the negative 0.2k. Solving for k. Any ideas on how we want to get started with this one? What could go first? I would say start with your 700. We can rewrite this if we want to, but 700e is the same thing as 7 times e raised to that negative 0.2k, right? Inverse of multiplication is your division. We got a base e, so I think natural logarithms is the one that we want to go with. E is our base. The 1/7 becomes our of. And the negative 0.2k becomes our equals to. You know, if you wanted the exact answer, again, base is understood to be e, so the natural log of 1/7 divided by 0.2. Therefore, 9.7. Maybe now that we see it, do we feel okay with that?
Is it a negative 0.2?
It should be, yeah.
So then would the answer be negative 9.7? Or still positive?
I think it's still positive 9.7. The natural log of 1/7 is going to make it negative. But you're right. I dropped the negative 0.2. I think I probably better walk through number 4 with you. 4 raised to 2x minus 7 equals 5 raised to the 3x plus 1. So variable and the exponent for both of them, so definitely want to use logarithms. Let's just use natural log this time. You can use either one, log or natural log. It's up to you. A little bit of space here for this one because it is a little bit longer. So I'm going to use the technique where we take the log or the natural log of both sides. Okay, I'm not going to convert it to log form in this case because I got an x on both sides. So that's kind of your hint. So natural log of both sides. Reason being exponent on both sides. 2 minus x. Even though it's an expression, it's still the power, so we can bring it down in front. So 2x minus 7, all of that, times the natural log of 4. 3x plus 1, same idea. 3x plus 1, all down in front, times the natural log of 5. Once again, variables now on the same playing field. We can work with it. And now we got to kind of move some things around. Actually, before we do that, let's go ahead and distribute. I'm going to distribute this natural log of 4 to both of those. So we get 2x times the natural log of 4, and then negative 7 times the natural log of 4. Same thing here. Let's distribute that natural log of 5. 3x times the natural log of 5 plus 1 times the natural log of 5, which is natural log of 5. Everybody okay on that? If that looks confusing, just put the natural log of 4 out in front and the natural log of 5 out in front, and then it's just your regular distributive. Some people call that the backdoor distributive, whatever. 4 terms, 1, 2, 3, and 4. 2 of those terms have the x, so we need to get the terms with the x to one side. Everything that doesn't have an x, get it to the other side. So I'm going to do this in one step. I'm going to move the 3x over here, all one quantity, so we're going to subtract that amount to both sides. Minus 3x natural log of 5. X is to the left, constants to the right, so now I'm going to add the 7 natural log of 4 to both sides. So we get 2x times the natural log of 4 minus 3x natural log of 5. Natural log of 5 plus 7 natural log of 4. All right, we're close now. What can we do on the left? First of all, how many terms do we have on the left? 2. What do they both have? An x, right? So this is no different than this. You've got, I don't know, 4xy minus 7x. What can you do here? Factor out that x, right? And by factoring out the x, it gets it from multiple x's down to 1. So x parentheses 2 natural log of 4 minus 3 natural log of 5. Natural log of 5 plus 7 natural log of 4. This is all one quantity now. So all you got to do is divide both sides by all of that. So x is going to be equal to natural log of 5 plus 7 natural log of 4 divided by 2 natural log of 4 minus 3 natural log of 5. Beautiful, right? A couple more that you might see. At first glance, what are your thoughts here on this one? Other than just maybe punt. What does this look like from 3-4 weeks ago? Kind of like a quadratic maybe? Okay, so I kind of see that quadratic taking place. I see the 2x, the x, and a constant. All right, so I'm thinking, how do we go about solving quadratics? Quadratic formula, factoring, maybe along there. But how in the world are we going to factor now when the x is in the exponent? Well, let's take a look at it. If we want to get it into standard form, it was something like that, where we had that 2 be the exponent. So I think what we want to do here, and hang with me, I'm going to write it first and then explain. Basically what we want to do is this e to the x is going to be our x. Once again, our a value is not there. It's understood to be 1, but our x is the e to the x. Now, how was I able to do x raised to the 2? Because it's like we kind of changed it. It was 2 times x. Well, again, the power rule states that if we got a power raised to a power, we got to multiply those two. So even though I've changed it, I didn't change the equivalency of it. Power to a power means multiply. 2 times x is still just 2x. Again, this is a specialty one. That's why we're going over it together. But this guy is just playing the role of x. So, you know what? Let's just go ahead and write it as that. Use the substitution. And hey, now things are a little bit more comfortable for us, right? So now as we look at this, if we were to solve it, maybe we could factor x factors of 14. Yeah, 7 and 2. I know that difference is going to be 5. So u is equal to -2 and u is equal to 7. Once we set it equal to 0. I shouldn't say u, I should say x. Ooh. Probably should not have used x. I should have used a u there, but that's okay. Now we need to replace this x with what? What did we do before? Or say? Well, e to the x is that. Thus, e to the x is equal to -2, and e to the x is that 7. This is called the substitution method, just different way than what you know it. Replacing that x with what we originally had it as. Let's go ahead and finish this now. I'm going to take the natural log of both sides. Natural log of base e to the x, what is this equivalent to on the left-hand side? Yes, it is. Everybody type in the natural log of -2 real quick. Whatever calculator you got in front of you. And what do you get? Something not good. Like an error, systematic error, syntax error. Not for sure what the TI inspires tell you. Long story short, can't do it, right? Reason being, you cannot take the log or the natural log of a negative value. Okay? So, we get to disregard that one. Only one that is true is natural log of 7. So this is kind of a specialty one. Keep this in your notes. Come back to it when you see it. You may see it once, maybe twice in the homework. Last one. Another equivalency here. This one's fairly basic. Once again, what do you suppose is true about x and y? Equal. Yep. So as we look at this thing, looks kind of complicated. Log base 2 of 7x minus 4, log base 2 of 2x plus 1. What has to be true here? They have to be equal to one another. The ofs have to be equal to one another. So yeah. Thanks, logs, but don't need you this time. Now, it's good practice. We're okay, but it is good practice once you get your variable. If your variable's in the of, we really should go back and check this just to make sure we don't get that negative of like we did up here with the natural log of -2. But if I plug 1 in, 7 times 1 is 7, 7 minus 4 is 3. That's positive, we're good. 2 times 1 plus 1, 3, we're good there.